Okay, let's get started. Let's talk about how things are going to work today and tomorrow. So you've got a mastering chemistry to do tonight. A lot of you worked on that and got most of it hammered out. A few of you still are waiting to start. So it's worth some points, and it's a shorter problem set. Even though 16 problems, most of them are pretty short to do. So there's a study guide posted if you haven't started looking at that. The other thing that I made available is a homework set for Chapter 10, and it's what I want to call optional. I told you all to do it for practice, but in case you bombed one, it's just going to be an extra assignment. So if you don't do it, it's a drop. It doesn't count towards you. But if you want to spend the time between now and Friday to do that assignment, so it's going to be, you have to Friday to finish that. It'll be an extra, it'll replace one, a low one. So if you got one you didn't do so hot on, you can do that. If you don't want to do it, don't feel you have time to do it, don't do it. It doesn't hurt you in any way. It's overall chapter 10, but it's a really short assignment if you take a look at it. So it's only about 40 minutes to do. So yeah.
Say we absolutely belong in chapter 10.
Absolutely not. Yeah, so you've got nothing to lose, even just to go in and look at it. Look at the question. So it's a bonus only, if you want to think of it that way. So it can hurt you in no way. I'd encourage you to at least look at it tonight in your prep for the exam, just to look at some of the types of problems, even though we're not going to cover some of the things. We're not going to get through everything today in Chapter 10. I will use part of the time the exam course is tomorrow. We'll finish that up after we do. We may get through the first 10 or 15, 20 slides, whatever we get through. A lot of it goes through pretty quick, but I'm going to use the last half of today. So 30 minutes till, y'all tell me we need to do exam review. If I'm, forget about it. So I'm going to give you the last 30 minutes to ask questions for the exam today. Okay? So then we'll come back up, and whatever material we get through today, that's all your thing you're going to be responsible for on the exam. Now, the other stuff's still going to be on the final exam, so I'm going to cover it. So we'll come back Wednesday and Thursday and finish some of that up. And then Thursday, we'll also do a review of the final exam. Yes?
Is the final going to be curved?
The final is curved in the sense that it's a national exam. There's 70 questions. And what I do is take the 70th percentile nationally and make that 100%. So out of the 70 questions, I think last year it's 42. You get 42 right, you get 100. My students typically do extremely well on that. So if you study hard, do well on it, I'll have many students, anywhere from 20 to 30% of the students are going to make more than 100. And I have students that make, I occasionally get a student that makes 55. You get 120 or whatever that is, 55 divided by 40, 50. So,
If you get more than 42 questions,
Is it like the starting
Absolutely.
42?
is it what?
Like the starting 42 questions? Or is it
No, it's of the 70 questions that are on the exam, they're all, yeah. So on their material that we're covering, there's a little bit of the material that's actually in Chapter 11 that's probably on the exam. But like when everybody teaches this, you can't cover absolutely everything. There's just not enough time in a semester. So everybody, regardless of what school you were taking it at, there's a little bit of material that you didn't cover. We've covered the bulk of what we need to see. So you've got a great survey this semester of everything that you need to see to be ready for that exam. There was another question. Yep.
I was in Kansas Thursday.
Yep. The exam is tomorrow. So I posted a study guide for that, as well as sent an email out about that as well. So take a look at your stuff on Blackboard, and you can look at that study guide and things that we had. Yes.
Is today the last clickers? Or will we do clickers on?
No, we'll probably do some clickers on Wednesday.
Okay.
So and potentially on Thursday.
Okay.
So I can't add those clicker points in until we finish that last thing up. So once we do the last day of class on Thursday, then I'll put your clicker on.
Okay, so we'll know what it is before the final.
Yeah.
Okay.
Yeah, and stay to your last lab back. So we'll take our exam on Tuesday by Friday afternoon. hopefully, unless we have some problems with we're starting our next round of chemos today. Unless I have some health problems with the person I'm taking care of, I'll easily have those in by Friday afternoon.
So the final doesn't go in with your other exam grades?
No, it's an independent grade itself, and it's worth 14% of your final. So it's where a regular exam is only worth like 9%. It's worth about an exam and a half. So it's certainly something you don't want to blow off. It's not a bonus opportunity. It's part of your grade. Yes.
When is the final again?
The final is Wednesday finals week. The 11th, yeah, and we'll do it at the scheduled time, which is, I forgot when it was. We looked it
It's at
up.
11.
It's at 11 o'clock.
Yeah, it's Wednesday at 11.
It's a week Wednesday at 11 o'clock.
And you can still buy those books, right? For the,
Absolutely. Those study guides, if you want one, they're $25. You can come to me or you come to the department secretary downstairs. She has them. So, yep, those are available for you if you choose to do that. Okay. Other questions? All right, so we're going to start talking about stuff in Chapter 10. Chapter 10, the things that we're going to be responsible for covering, and there are several things in the chapter we're not going to do. We're going to do what's called VSEPR. It stands for valence shell electron repulsion theory. Look at the 5 basic shapes of that, then look at the influence, and we have lone pairs. And from that, we want to learn how to predict molecular geometry. That's probably where I hope to get through today, and then we'll look at ending up with shape polarity. Again, just a handful of problems. I suggest you take a look at those as well as the mastering chemistry. Okay, I showed up today. All right, all in? Or now? Okay, so yes or no, you got it right. So if we look at, there's a resource that's available for you, and next semester I'll go over this in detail if you want to look at how to utilize it. This software is called ChemSketch. It can aid you in making these 3-dimensional drawings, and it'll even do some optimizations. It's by no means a required thing, but when you get to higher level chemistry courses like organic chemistry, you need to sometimes draw structures for a report or something. It's also a structural drawing program. So it's got some neat things, and it's free, so nothing wrong with free. So here's the key thing, is that structure determines property. I've talked about that. There is a good introduction in the textbook in Chapter 10 talking about hemoglobin, and something I've already talked to you about. When we talk about the structure, things that play a role include the arrangement of the skeletal atoms. So like when we drew Lewis structures, what's attached to what, the types of bonds that form, not are they just polar, or are they covalent, or are they ionic, but also are they a polar covalent or a non-polar covalent? That depends. And one of the biggest things that controls function is shape. So what is the 3-dimensional shape of a molecule? So if we look at what we can learn from bonding theories, what we'd like to be able to do is predict something about the shape. What does something look like? So now we have to start thinking about things instead of being on a flat piece of paper. We have to think about molecules as being 3D objects. And here's where we vary. Some of us, the way we're made, we can see 3-dimensional things in our head much easier than others. The same way some people love math, some people hate math. Some people have a visual perception to understand and to grasp things in 3 dimensions easier than others. And there's no way around it. You either have it or you don't. And if you don't have it, you can figure it out. You just may have to put more effort into it than somebody else. So when we start talking about shape, we're going to relate things to common geometric figures like triangles or pyramids, things that we're familiar with. The idea is that the corners of these shapes indicate places where surrounding atoms are going to be, and the central atom, okay, it's the one who's determining the geometry. It would be in the center of whatever this geometric figure would be, whether it's a triangle, a square, or whatever it may be. So from that, we can estimate or determine what bond angles would be. So bond angles represent the angles between three connected atoms. Now, I told you the story of hemoglobin. It's a protein. It's got a mass about 65,000. It's got approximately 300 amino acids in it, and there's a lot of variations in the body, but small changes to it yield to some very critical diseases. So one of them that's an important one that influences certain populations is sickle cell anemia. Okay, so sickle cell anemia occurs with certain genetic groups, and in that there's a genetic disorder that causes the hemoglobin to have a slight twist in its shape, which causes its function to decrease. Another one that I mentioned earlier is Bart's disease, and it is typically fatal for children that get that disorder unless they're kept on oxygen the rest of their life. When you start looking at molecular genes, they're big things. Okay, 300 amino acids put together, you've got this huge thing that has a molar mass now of over 60,000. It's got, go back to its formula, it's got almost 3,000 carbons, 4,500 hydrogen atoms, all these oxygens, nitrogen, sulfur, and iron. All this thing comes together in this delicate balance where these are the places where hemoglobin carries oxygens, called the heme groups. There's 4 of those embedded in the structure. And if you start to tweak it just a little bit, you can go change one amino acid in here at some point, make a mutation. It causes the structure to tweak or bend just a little bit, and all of a sudden the molecular machine doesn't work quite like it should. And that's the result in diseases when you see things like that occur. All right, so there's a lot more information in the text than what I just presented you with. We want to know about the fundamentals of how we can use Lewis to predict these shapes, so the Lewis theory. So the Lewis theory looks at 2 different types of things around a central atom. We're looking at the shared pairs of valence electrons between bonding nuclei, and we're looking at the unshared valence electrons around the central atom. Okay, so that's the idea, is what we want to look at, those 2 things. How many shared pairs are around the central atom, and how many unshared pairs around the central atom. And the other thing is the types of electrons. We don't care about how many core electrons are in there. We care about valence electrons. But it's because it's the outer shell electrons that determine bonding geometry. Okay, so from this we can predict the fundamental shapes. We know that negative charges want to be away from each other, so they're going to organize in a way that those negative charges are as far away from each other as possible. So the idea that we take and look at the electron groups surrounding a central atom and we're place them as far away apart from each other to give us the most stable geometry. This is called the valence shell electron pair repulsion, which we abbreviate as VESPER. And the things that we learn in VESPER in this chapter, you'll use throughout chemistry, regardless of how far you go. So if you go into Gen Chem 2, we're going to start Gen Chem 2 with using VESPER to learn things about why molecules behave the way they do. If you take organic chemistry, you're going to use VESPER to understand 3-dimensional shape. If you take biochemistry, you're going to use VESPER to understand why things make the shape that they do, going from things like cholesterol to lipids and fatty acids, to bond polarity, and to macromolecules like large proteins such as the hemoglobin that we just talked about. Okay, so the idea is that we should come up with a way that allows us to get some rough prediction of shape and bond angles. Now, this is the most elementaries of theories. As you take more advanced classes and your junior and senior year in chemistry, you'll find that there are more advanced models that you can use. This is our simplest way. Okay, so here's the idea that you have a central atom. In this case, it's surrounded by 3 bonded pairs to 3 external atoms. So central atom, external atoms, and these electrons are shared between the external atoms and the central atom in what we think of single bonds. And they could be single bonds, could be double bonds, could be triple bonds. It just matters that they're shared pairs of electrons. Now the thing is those electron pairs are all negatively charged and they're all trying to get away from each other. So the groups are going to organize each other in a way to maximize this repulsion, and if we were to take and set it up and look at a way that they maximize repulsion with three things bound to a central atom, what happens is they all end up in one plane. Okay? And they form the corners of a triangle. Okay? That's the shape that it would take. And that minimizes the repulsion. Any other place that we would take and bend them would increase the repulsion and increase the potential energy. This is the minimum potential energy shape. So when we take and look at the electron groups, we're looking at the valence electrons around a central atom, and we want to know how many lone pairs are electrons. And what happens is one electron group counts as a lone pair. So you can either have one lone pair in the example of this Lewis structure below, or you could have multiple lone pairs. Okay? So 2 and possibly even 3 lone pairs. And in some cases, you could even have 4 lone pairs around a central atom. All right? Each bonded group counts as an electron group. And the important thing is it doesn't matter if it's a single bond, a double bond, or a triple bond. So in this example, the single bond nitrogen to oxygen counts as one group. The double bond nitrogen to oxygen counts as one group. So what we want to do is to identify this organization around the central atom. And the way that we name this, in this example, it's got a lone pair, a single bond, and a double bond, is we call the central atom A. The attached atoms we call B, and we simply put a number for the number of groups that are attached. So in this case, there are 1, 2 things attached. We call it an AB2. And the E represents the number of lone pairs. So when we name this thing, we would call it an AB2E to represent this geometry of a central atom, 2 groups attached, and a lone pair. And it doesn't matter what the atoms are. It's an AB2E. So if I said something then was an AB3E2, just in terms of a Lewis structure, that would represent a central atom with 3 things attached to it. We'll work on shape in a little bit. And it has 2 lone pairs to it. That's what an AB3E2 would represent. It doesn't matter if these are double bonds, or single bonds, or triple bonds. Okay? We're not concerned about octet rule here. We're just concerned about the number of things attached to the central atom. Okay.
What's the number for the EB if it has to have radical?
Okay. Still, it counts if it's a radical. That's a great question. It still just counts as one group. So it doesn't have, even if it's an unpaired, it counts as one group because it's still in that one set of world. Okay, that's a good question. Nobody's ever asked that before. Okay, so besides being here today, what are the electrons that are important? So when you determine this electron geometry, which electrons do you need to consider? Need answers. Last 2. All right. Anybody else? We're all in. Pretty fair step. The predominant answer is B, though. More of you chose that. And the ones that we need to consider are only the electrons around the central atom. Okay, so I'm not concerned about electrons here. I'm concerned about only the things that are shared around the central atom. Those are the ones that determine the electron geometry. So I don't care about the inner electrons. I don't care about, only thing is the valence electrons that are out there. Those are the ones that determine the geometry in these things. All right, so here is a simple one. So tell me this is an AB E who? What would this guy be? So I gave you the Lewis structure. And while you're answering this, if you can't write Lewis structures, it doesn't matter if you draw these or not. That's the first thing you have to be able to do is come up with a Lewis structure. So that goes back to the chapter 9 stuff. It's 8, 9, and a very, very small, what we covered today in 10. Yep. All right, 3 more. Last one, we're in. All right, so almost all of you said C, and C it is. So you've got the central atom, 3 things connected to it. So that's the AB3. So this is our A. These are the B's. There's 3 things attached, and this is our 1E group. So A, B, 3, and then E. If it's E1, you don't have to put a 1. Yes?
Unlike the hydrocarbons that have multiple chains of carbons,
Yes. You have, if you, and we'll look at towards the end of the chapter, if you have multiple central atoms, you go 1 central atom at a time. So when you look at something as complex as the hemoglobin, that's where VSEPR becomes very complex, because you've got over 3,000 central atoms. But you have to go 1, you have to find the end of the chain and start working your end 1 at a time. Yes? Well, since we're treating it 1 atom at a time, it'll always be considered around only 1 thing. You would never have an A2. It could be, you can have multiple B's, but you only have 1 central atom, because we have to think about 1 at a time. Okay? Those are good questions. Okay, so it comes down, there are 5 basic geometries that we're going to learn about today. And what these 5 basic arrangements are is they assume that there are a maximum of 6 bonding electron groups. Now, if you take more advanced chemistry, like inorganic chemistry, and you look at very large atoms, you'll find that there can be more than 6 bonding groups, but that's the most common thing you see is up to 6. They'll get through the main group elements. But when you get in the center of the periodic table, these guys in the bottom, you'll have things that can be more than 6, but that's pretty rare. So of these 5 basic arrangements, it results in 5 basic shapes. So like a triangle, that's going to be one of the shapes. We're going to need to know these 5 different molecular shapes that we could have. And we talk about what the bonds would be in terms of perfect geometries. For it to be perfect, everything has to be equivalent. So that means all the atoms have to be, exterior atoms would have to be the same. If you change one, that's going to shift this perfect bond angle just a little bit. We're going to maybe look about how to predict that. For things that have resonance, so we don't know which Lewis structure to write, it doesn't matter because the electron geometry would be the same. Let me go back and show you the example of that. So if I were to go back and look at this guy, and there it went. So it wouldn't matter where I put that lone pair or the double bonded pair. If I were to write it to the left or to the bottom or to the right as it's written, on any of these, it's still the same geometry. Regardless of any of which one of those it is, it's still in AB3E. So that resonance doesn't matter. So you don't have to worry about getting that perfect when you put these things together. It's still going to work out for you. All right, let's look at the first and the simplest of the shapes. So if there are 2 electron groups around the central atom, and this is how we figure out what it is. How many electron groups around the central atom? That's the first question you have to answer. If it is, it's what we call a linear geometry, and the bond angle is 190 degrees. So examples are beryllium chloride. So it's an AB2. So there are no lone pairs, and there are 2 things attached to the central atom. And if you've only got 2 things attached, the way that they can be furthest apart is a straight line. Okay, so that maximizes the repulsion between these electron pairs by keeping them exactly opposite of the central atom. The same is true of carbon dioxide, CO2. Okay, here's its Lewis structure. It's got 2 double bonds, but it still doesn't have anything lone pair bound to the central atom. So it's also an AB2, and it has a bond angle of 180 degrees. Yes?
So do all of those not have?
Everything's an AB2. That's what characterizes that one. Now, we'll look at other things that are going to, but that's what makes this geometry. Okay, so that's just one of the 5. So we're going to build the other 4 and put those together now. Other questions about an AB2? All right, so that's the simplest one. The next is to put 3 groups on. And when you put 3 electron groups around the central atom, it takes the shape of a triangle. So much like the one I've already shown you, the bond angles are going to be 120 degrees. An example of that is boron trifluoride. So it also has an incomplete octet. So boron trifluoride's Lewis structure, 3 things bound to the central atom, no lone pairs, so it's an AB3. So in 3-dimensional space, this is laying in one plane, the plane of the board, and it's got the 3 atoms attached at the corners of a triangle, if you want to draw the triangle out. So that means the bond angles are a perfect 120. Okay. AB3 is called trigonal geometry, and it's got a 120 degree bond angle. Now, if I add a lone pair of electrons to it, different story. Okay, so if it's an AB3E, it's different. So we'll get to that. All right. Now, if things are not all equal, we find that the geometries are not exactly perfect. In this example, a C attached to 2 hydrogens and then double bond oxygen. Now what happens is that the extra electron density that's in this double bond versus this single bond gives it a little bit more repulsion or pushing power, pushing away. It causes this bond angle to be slightly larger than the perfect 120. And as it squeezes these down in together, this one is slightly less than the perfect 120. It's still pretty close to 120. It's off just a little bit. All right, but it's still lying in one plane, the plane of the board. All right, 4 electron groups is what we call tetrahedral around the central atom. So tetrahedral, that means that there are going to be 4 electron groups around the central atom. It's going to be an AB4. And an example is a carbon in its common binding pattern with 4 things bound to it, all single bonds. So in this case, carbon tetrafluoride. So 4 things bound to the central atom, no lone pairs. Now 3-dimensional comes into play. So for that to occur, the shape that occurs is the bond angle becomes 195 or 109.5 degrees. So the way this looks is like a 3-sided pyramid. All right, so if you wanted to imagine a 3-sided pyramid, I'm going to try to see if I can connect the dots. It would be a 3-sided pyramid that forms, and this one in the background would be that backside. That's the bond that would form in the central atom, the carbons dead in the center of that 3-sided. Okay, that's called a tetrahedral, and the bond angles that form here are 109.5. So the bond angles would represent an exterior atom to the central atom to an exterior atom. And it's this 109.5. And it doesn't matter which set of bonds you look at, they're all 109.5. The classic example of the smallest hydrocarbon is methane. CH4. So methane is CH4. It's the simplest hydrocarbon you can have. Now, we've been drawing figures like this for Lewis structures, but that doesn't really represent what's going on in 3-dimensional space, because now it has this tetrahedral shape associated with it. So if you want to think about how do you show this now think about it in a 3-dimensional shape, and here's, hopefully you start to see this. You've got these 3 carbons, or these 3 atoms in one plane, and then in another plane, you've got these 3 atoms. So we have to start looking at it. If we look at this one, if I consider what's in blue in the plane of the board, what's in green is one of the atoms that's coming out of the board, the other atoms is going back into the board. We start looking at it in 3-dimensional space. Okay, tetrahedral shape. All right, so that was the 3rd one. Now let's create the 4th group. So that is when you have 5 electron groups around the central atom. Now what happens is the shape is that you have two tetrahedrons that are base to base with the atom in the center of the tetrahedron. Don't worry if that doesn't make sense. We'll come to show you what that is. So the resulting geometry is called a trigonal bipyramidal shape. So now we have positions that are unique or different from one another. So let's just so you understand what I'm talking about. So now it's like you have a triangle. So you've got one pyramid above. So that would be one pyramid, three-sided pyramid. And then you also have one that's below. So now you've got two three-sided pyramids. And then in the center of it, you put your central atom. So your central atom is going to be in the center of this guy. All right? So there are 5 things bound to it. So I've got 1, 2, 3, 4, 5 things bound to it. That's trigonal bipyramidal. So now we have to make a distinction on where things are bound. We have things above and below the central atom. We call that the axial position. Right? And the things that are in the same plane as the central atom, going left and right, are what we call equatorial positions. And the reason it matters is because we look at the bond angles are not all the same on these guys. So the bond angles are slightly different. On this, you can see pretty easy, this bond angle is going to be a 90 degrees. Okay? But if I look at the bond angle in this one, that's a trigonal planar, so that one's 120. Yes? If we go, well, it depends if you're talking this atom to central atom to the other axial, yes, they're 180. And mine's a little crooked there. But if we look at axial to equatorial, they're 90. So the two 90s would be the 180. The true right angles. Yes. It's always a reference. That's correct. Yes. We're always comparing back to the central atom on these. Okay, so the bond angles between the equatorial positions, that's the ones that are in the planar, trigonal planar, those are 120. And the axial to equatorial are 90 degrees. If you want to think of axial to axial, they're the 180. All right, so here's a better picture than I could draw. Here's an example of something that's trigonal bipyramidal, phosphorus pentachloride. If I look at its Lewis structure, draw it out. I've got the phosphorus atom with 5 things attached, no lone pairs, so that's an AB5. Here's what it looks like in a 3-dimensional sketch. All right, so if I take the triangles of it, so if I add those back in, I've got a triangle for a pyramid that's forming above and a pyramid that's forming below. All right, so that is trigonal bipyramidal geometry. 5 things attached to the central atom. Last one, octahedral. So octahedral is now when we have 6 electron groups around the central atom. Now what happens is it's 2 square-based pyramids that are base to base instead of 2 triangle-based pyramids like we just had. So you're going to take, and this is easier actually to draw, you would take and draw what represents a square, okay, in 2-dimensional space, and you're going to have the central atom, and you're going to have 1 atom above it, 1 atom below it. So these are your 4-sided triangles. So you would have atoms at every corner binding this together. Okay, so if we look at how many different atoms are in this, there are 4 in the plane here, 2 above, 1 above, and 1 below. That means that's the 6 things that are bound to it. Okay, so that means that this particular figure of an octahedron has that name because it has 8 sides to it. So if you 1, 2, 1, 2, 1 are over here, 3, 1 to the back's 4, and you got the same copy of that on the bottom. That's the 8 sides to an octahedral. So it's an 8-sided object, and all the positions of this guy are equivalent. All right, so the bond angles are a perfect 90 degrees. Now my drawing doesn't look so sweet, but it's easier to see with this one. All right, so here is sulfur hexafluoride. So it's an AB6 geometry. No lone pairs, 6 stains bound to the central atom. All right, so this you can see a lot easier. Here everything's in the square planar, and it's all 90-degree bond angles, one perfectly above it, one perfectly below it. Any combination you look, it's a 90-degree angle. All right, octahedral. Okay, now if we got to end there, it would be super sweet and easy. Problem is, sometimes lone pairs come into play, and more frequently, lone pairs come into play. So when atoms have, the central atom has a lone pair, we have to make an adjustment and see how that comes into play. So with lone pairs, the lone pairs occupy space even though there's not an atom there. And if we look at an atom, we can't see electrons, where electrons are. We can see nucleuses, but we can't see individual atoms. So their electron density takes up space just like a bonding group. Now what happens is that lone pairs, because their electron density is not shared with anything else, their repulsive force is a little bit greater than the other repulsive forces. So when we look at this influence and deviation from ideal on bond angles, the lone repair repulsion is the greatest, then a lone pair bonding pair, and then finally the least repulsion is a bonding. And this influences the bond angles to make them a little bit smaller than we expect to be. So if I wanted to figure out what was the ideal bond angle for the carbonate ion, so the first thing I've got to do is I've got to draw a Lewis structure out for carbonate. So let's do that right quick. So carbon's got how many electrons?
4.
Okay. The oxygen, there's 3 of them. Each oxygen has how many? 6. What I do, it's a -2 anion, so how many electrons do I put on that? Okay, so I would add 2 for the -2 charge. So 4 electrons, 18 electrons, and 2, so that's equal to 18. So I get 24, is that right? All right, 24 electrons. So I compare carbon and oxygen. Carbon is the least electronegative, so it's going to go in the center. So first thing, we got to get a Lewis structure drawn. All right, so we got a Lewis structure. Now I'm going to start connecting. So I form the single bonds first, and again, this is a polyatomic ion, so these are some -2. So I had 24, now I've used 6, so I'm down to 18. Now I want to try to fulfill the octets of the external atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm out of electrons. Does everybody have an octet? Nope. Okay, so to make this a more appropriate Lewis structure, to give everything an octet, I would take 1 electron pair and collapse it in to make a double bond here. Now does everybody have an octet? Okay, it does. So now, based on that, I could write my ABE thing. So this is a who? An A, B, how many? Okay, E, any, 0. So this is an AB3. That tells me this is trigonal planar. Okay, and if trigonal planar, what's the bond angles? Ideally, it's 120. So all these bond angles are common at 120 degrees for trigonal planar. You're going to be asked to do something like that on the exam. Okay, so you have to do the Lewis structure first. From the Lewis structure, you can figure out the identity, and from that, you're going to have to know what the bond angle is or the geometries. Now, we describe this as 2 different terms. We describe it in terms of a molecular geometry. And if you look at the old exams, you've seen this. I'm just trying to bring it up now, versus an electron geometry. So electron geometry includes lone pairs. includes the E's, the lone pairs, if any. The molecular geometry is only A's and B's. Okay? So as we look at these, this one doesn't have any lone pairs, so the molecular geometry and the electron geometry are equal to each other. So the EG electron geometry would be equal to the molecular geometry, MG. But there's going to be times when we look at it, that there's lone pairs, we don't, when you look at the molecular geometry, you don't see the lone pairs. If it's what now?
It was a test question for me to write the 123 page.
It'll ask for it. So sometimes I'm going to ask you questions that ask for the geometry. Sometimes I ask for the bond angle. Sometimes both. So you'll see, if you look at the old tests, you'll start seeing those. Sometimes I may have that it's trigonal planar is your only option, and then I may put 120, 180, 90, and you're going to have to pair them both up. So you need to go both ways, honestly. Okay, anything else on that one? All right, so I'm pointing at a particular atom here, and this is aspartic acid. So it's a simple amino acid. And based on that one particular carbon atom that I'm pointing at, I want to know what is its electron geometry. So the way that you answer it is an AB what? Okay, how many things are attached to it? AB what, E what, and then based on that, you choose is that which one of these things? Is it linear, tetrahedral, trigonal pyramidal, trigonal planar? It's just visualization. Let's do. All right, so mixed between two predominantly. Part of you said A, part of you said B. One person said choice C. Okay, so we've got this one central atom here. Choose a different color. Concerned about this guy. All right, if I look at what's attached to it, I've got 1, 2, 3, 4 things that are bonded to the central atom. No lone pairs of electrons. That's an AB4. So I just need to simply know what is an AB4. An AB4 is a tetrahedral. Okay, that's the way you answer that. All right, if I were to point it at one of the different atoms, so let's say I would have pointed at this guy. All right, and I wanted to know what its electron geometry is. This would be something that's a little bit cheating because this particular atom, it's not showing you the entire Lewis structure to know that this one is an AB2. That particular atom is an AB2E2. Right? That was irrelevant for this one because there's no lone pairs on that atom. That's the reason I gave you that one. But if I wanted to know the electron geometry to this one, okay, it's an AB2E2. So the thing I told you about electron geometries is that it includes both the things that are bound as well as the lone pair. So even though its molecular geometry is not the same, its electron geometry is also an AB4. So it would be the exact same thing. It's tetrahedral. Right? So it's looking at there's 4 groups bound to the central atom, even though 2 of them are just electron pairs, it would have the same geometry. Okay, so an octahedral. So I told you about octahedrals. What's the ideal bond angle around octahedrals? So you got the central atom in the center of that, 2 sides of pyramids. What's the bond angles around those? Okay. so we're all in. Almost everybody said choice D, and I like choice D. So, yep, it's 90 degrees. All right. That's just a review of the Lewis structures. I'm going to skip that. All right, so when we look at the influence of lone pairs, I'll tell you what, that's just, that's going to be our stopping point. So this is where we're going to be up to in the notes today. Make sure, yep. So when we start going to these derivative shapes, the things up to this in the notes are what you're going to be responsible for. So up to this, that's a slide from the last chapter. So knowing geometries, with that, that's where we're at. We're going to talk about the influence of lone pairs on Wednesday, and on Thursday, finishing material up. But this is what you're going to know for the exam. So I'm going to give you the rest of the class period for us to do review. Okay? So not everything in Chapter 10, even though the material we're going to cover, is going to be on the exam, only up to that. All right, so save that, make a new one, and I'm assuming we want to pull up some old test questions. Old exams. All right, so I've got the last 3 years worth of exam 4s. And again, we did 1 day on exam 10, or chapter 10. You're going to have at most 3 or 4 questions out of chapter 10. Okay, and maybe 1 on the back. You need to emphasize your studying on chapters 8 and chapter 9. What we got?
Number 6 on 2016.
Okay, 2016, number 6. All right, so that one. All right, so on number 6, it says choose the orbital diagram for the ground state of the selenium 2- anion. So here's where we have to understand our electron configurations and how they match up. So if I look at selenium and find selenium in the periodic table, it's right here. Okay, so if I look at its valence electrons in its valence shell, it's in the 4 period. So it's 4s2, 4p4. So 4s2, 4p4. That's its valence electrons. And then below that, I've got a shell of argon. Okay. So, but this is not neutral selenium. It's a selenium 2- anion. So it's got 2 extra electrons to it. So when I add those 2 electrons, they add to this guy. So now that becomes argon, 4s2, 4p6. So if I show in the orbital diagram that electron configuration representing the 4s and the 4p's, I've got 2 electrons here, and I've also got a full p shell. So unless there's something that's a duplicate, twisty. It's got a full octet. And that's what's going to be true on almost all of the ions when they react. They're going to react to gain or lose electrons so that they achieve that full octet. Now the neutral atom would be different. So if I ask for the neutral atom, if I ask for selenium itself, so instead of the selenium 2-, ask for selenium, and it just had these 4 electrons, then this would have been the answer for selenium neutral. But it's the 2-. Okay, what else? 10 on 17, correct? Okay. All right, 17 from the 10. All right. So we want to look at what's going to be the last quantum number, or the last electron added, and the four quantum numbers for strontium. So if I look at strontium's valence electrons, so strontium is right here. This last electron added is the 5s2. So the last one is the one that's 2. So if I look at the orbitals, that the 5s1 electron in the 5s would be the one that's a plus 1/2. So this last one that's added would have an m sub s of a minus 1/2. Then if I look at the values that we would have for all the other ones, so the first quantum number is n, so it'd be n equals 5. That's the 5s. If n equals 5, L can only be 0, and m sub L can only be 0. Okay, so if I look at the one that that matches that, I don't see anything that's a match for that.
Can you explain away?
Yeah, and the reason that I would have said something in the class about this, or either that or corrected it in class. This last one is plus 1/2 or minus 1/2. It doesn't matter if you write the up arrow first or down arrow. Okay, it's just by convention we write the first one, but they're degenerate, means they have the same energy level. So it could be the plus 1/2 or minus 1/2, but all of the other ones it can't be, by convention of it's the L equals 1. Well, I didn't have to do the full configuration. I could just look at strontium's here. This is the N number. Okay, so that's N. These are the S electrons. So just knowing how the periodic table matches to electron configuration, that told me this information. And then thinking about it in terms of where we are in the orbital diagrams, that's the 5s orbital. I've only got 2 electrons to put there. One's got to be up, one's got to be down. Yes?
So you know L could equal anything from 0 to 4, but you know it's 0 because it's S
Yes.
shape, right?
Yes. So when we go back to that's what L's tell us. If we go back and just review that, L equals 0 is an S. L equals 1 is a P. L equals 2 is a D. And L equals to 3, it's an F shape. That's what those L's mean. All right, and M sub S can be a minus L to plus L, including 0.
How do you dictate the M of L?
How do you dictate the M of L? All right, so let's say that, let me just make one up. Let's say that I had an electron that was the 3d6. All right, so let's say that's my last electron. So if that was it, N would be equal to 3, and then L, if we think about L could be a minus.
N would equal 4. No, I'm sorry.
Say again?
Yeah, N would equal 4, right? Because it's in 3d10 is the transition metal on the cube.
Okay, well, it's actually the D. It depends on which one you're doing. So this is the D's
Right.
that go with the 3s.
Right.
Okay, so if I'm doing this one, this is the 3d10s. So if you look at you got to go back to thinking when you start to fill them. So 1s only have S's, 2 have S's and P's, 3s are the first ones that have the D's.
So it's still under, N is still 3 in that situation.
Still what now?
So your N is equal to 3 in that situation.
Yes. Yep. So the thing is that when you fill them, you fill in a way that, and I'd have to put the 4 F's in here. I on space. Okay, so this is the first one that has the D's. All right, so now going to the values for L, it's N minus 1, so it could be a minus 1 or minus 2, minus 1, 0, plus 1, plus 2. So the way that we'd represent that in the orbital diagrams for the 3D, 1, 2, 3, 4. All right, so we would have the 3D, and if we want to think about going left or right, this would be the minus 2, the minus 1, the 0, the plus 1, the plus 2. So I've got 6 electrons. So I put one here, 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 and here. That's the first 5, puts 1, and the next electron would go here. So if I were absolutely going to say what were that electron's valence or quantum number, I would say it's N equals to 3. It's L equals to a minus 2. M sub L is equal to a minus 2. And M sub S is equal, if you go to plus 1/2, the next one would be, last one would be minus 1/2. Now, the thing is that we typically don't, because these are like the spins, these are degenerate to the same energy level, anywhere in the D's, we don't restrict it to say that it's any one of those. It can be any of those. All right, so any combination that had the L equal to any of those values is an acceptable quantum.
I thought the notes said that L could only equal 0 to N minus 1. 0 to N minus 1.
N minus 1. So,
You wrote the.
I wrote the M sub L, sorry. These are the M sub L's, not the L's. L's is N minus 1. So these represent the M sub L's. Okay, so these are the M sub L's down here.
So
L is 2, 1, or 0 are the possible numbers for L.
So in your quantum numbers on the bottom, you said N3 L negative 2, it would be 2, right?
That's correct. Yeah. Oh. Absolutely.
That's the other one.
Wrong one. Yeah, getting there. It's Monday.
And we know that M sub L was negative because it was the first negative electron that you put into that valence.
Well, we by default you would say it's that guy, but we don't know 100%. I mean, that's what I'm saying. These are all equivalent to one another. So we say it could be any of those or possibility of the M sub L.
So what?
So when you've got multiple choices, you can't say absolutely is what it comes down to. Now, if it's the L equals 0, there's no option because the M sub L is only 0. It simplifies life, like on the last one we looked at. But when it's the other ones, you have to look at what are the possibilities, right? And then the thing that you need to be able to recognize is what's not a possibility. Okay, choosing one that doesn't make sense. Okay. All right, I confused myself on that one, so thanks for correcting. Okay, so which other ones?
On 17, can you just explain 16?
Yeah. This is something you certainly need to know. So which element can expand its valence shell to be more than 8 electrons? So one of the things that we talked about in chapter 9 were exceptions to the octet rule, and there were certain things that could and certain things that can and certain things that are common. The things that are in period 2, these guys are nevers. Anything that's in that one, that can never have an expanded octet. Okay, so that lets me rule out A, B, and C. Okay, so the ones that can have an expanded, so sometimes are these guys, and these are the commons, most common, for krypton and xenon. All right, so on that one, it'd be sulfur. Sulfur can have an expanded octet. It can have more than 8.
Is it because this was an odd number?
No, it's just the fact that it's got empty D shells, and those D shells can pick up the extra electrons.
So where is that region from again? That can.
Okay, so yeah, it's gonna be easier. There's a slide that I gave you the periodic table. These are the nevers. So 5 through 9 are nevers, and then this down below it are the sometimes. They include the halogens, and these are the krypton and xenon are the most frequently expanded octets. And again, that's a slide in our notes. Okay. What else? Joe. 27.
27 on 7.
Okay. All right, they're going to help me another one of those. Okay. 15th electron, and we'll do more of those. Maybe I'll get it right this time. All right, so the 15th electron in phosphorus, and phosphorus has 15, so it's the last electron, same type of problem. So what are the complete set of quantum numbers for that guy? So if I were going to write it out. So quantum, if I look at it, it's in the 3, and then it's got 3 s2s full, and then it's got the p electrons. So it's 3 s2, 3p, 3. So the last electron is this third electron in the p's. So I've got 3 s's, and I've got the p's, and I got the 3 p's. And if we follow the Aufbau principle, we put 1 up first, and then that would be the third electron in the p's. So this is the guy I would like to assign a quantum number for. All right, so all right, trying it again. So n equals 3. All right, if n equals 3, and this is in the p's, L equals what? Okay, L equals 1. So if it's, remember, L equals 0 is S, L equals 1, it's the p's, L equals 2, it's the d's, L equals 3, it's an F. All right, so the values we could have then, so these represent the m sub L's, would be -1, 0 to +1. So on this one, I would say m sub L would be equal to +1, but in reality, all of those are acceptable, okay, because they're all equivalent energies.
How'd you know L is 1?
Because it's a P. L equals 1 is equal to P. That was what we did on the last slide. Okay, so I'm going to go back to where we did this a couple of slides ago. So we got to know these guys.
Yeah, but on there, how'd you know?
Because it's a P. So we go back and look in the valence of the electrons. So this is a 3p, 3p3. This is the p orbital. The fact that that's a p makes it L equals 1. All right, and then when I do the m sub s, the m sub s values, we're putting the up one. Most traditionally, we put a positive 1/2 for the first one, but the reality is that it could be plus or minus 1/2. It could be up or down. And I would accept any of those, or any of those as correct answers on that.
So what if it's for the 12th one?
Okay, so if it's the 12th electron, then you absolutely, that's a very viable question. You would just need to go back to put the 12th electron in. So 12th electron is 15. That would be the 3p1. Okay, that would be that electron. That's the 14th. So it would actually be the exact same set of answers as possible. But if we do that one, it would be this guy going in first, because we're talking about 3p1, we're putting in this electron. So that would be the -1. So n equals 3, L equals 1. And I would say it's a -1, but again, I would accept any of those. And then it's a up, so I would say it's a plus 1/2, but their equivalent would be plus or minus. Yes?
The 12 electrons, the
3s, that was 13th, sorry. That would be the 13th electron. You said 12. So that would be the 3s2. of electron. So if we're going to do the 3s2, let me do it in a different color. So if we're doing this guy, you got up one and down one, we're doing this down one. So n equals to 3. And if it's in the S, what's L equal to? 0. That means M sub L has no option. It has to be 0. And the convention is, since that's the down one, it would be a -1/2, but in reality, they're equivalent. So I would take up plus or minus. Okay. What else?
Number 4 on the 16.
16, number 4. All right, so the number of valence electrons in cadmium. Is that the correct problem?
Yeah.
All right. Okay, so find where cadmium is in the periodic table. It's right here. Okay. So if I look at the number of valence electrons it has, so if I write out its electron configuration, so first I'm going to go, bless you. So I'm going to go back to the shortcut at the noble gas. Right. So I'm going to go back to krypton. Right, and then I'm going to add the krypton. And then going to krypton, the next ones would go to in here at the 5s2. And then where are these electrons that are going through here? Okay, so that's the 4d10. Okay, so the valence electrons are the outer shell electrons. Okay, so what would you think the answer would be? 2. Yeah, on the outer shell, it's the largest number for N. There's only 2 that are on that valence shell. The furthest shell out, even though these are filled afterwards, that's the furthest distance out from the nucleus. There's only 2 there. Okay, what else?
Can you just tell us what is going to be on the exam? Like, can you go to 2016 and just say the last page? Is it going to be on there more interpretation
Which one now?
of 2016 and 2017?
Yes. Okay, so 2016. Everything. All of the multiple choice. There's nothing covered there that we wouldn't cover. Absolutely everything in 2016.
Okay.
And because it didn't go into chapter 10 in 2016. 2017's first year we included chapter 10. So going to 2017, formal charges. So like the question number 21, where we're talking about the influence of the long pairs, the seesaw geometry, we haven't named that yet. So we haven't done that. 22 would be something we did do. The number of electron groups and the base geometries, yes. 23, we talked about the difference between electron and molecular geometries. I talked to you just a moment ago. 24, use VSEPR to predict the molecular geometry, yes. And 25, yes. So all except for number 21, the multiple choice. And at the end, this guy has lone pairs around the central atom, and we didn't get to cover that. So you may have one like 28, but this is an AB2E4. We haven't covered how to do an E4 yet. So an AB2E4. So
You said we do?
23. Yes, we talked about the stuff in 23. I talked about molecular and electron geometry before we go. Wrote wrote it on the bottom of the board. So yes, you're responsible for them doing that.
You do number 24.
So, okay, let me make sure there's nothing else here. So, yes, everything else, you wouldn't be responsible for 31 either because it has lone pairs around the central limit. So, we haven't got there yet.
Okay.
We'll cover that on Wednesday. Okay, do number 24. All right. So, okay, so let me do the little structure right quick. So I've got nitrogen, and oxygen. So 5, 5, and 6. I got 16 electrons. And I tell you the atom organization is this. So connect those two together. That gets rid of 4 electrons, so that leaves me with 12. Go to the exterior atoms, and I'm going to use everything up. So that gets rid of the 12. Now the problem is the central atom doesn't have an octet at all, so I've got to try to fill that so I can collapse a pair from this one and make a double bond. And that gets rid of that one. And I could do the same with the other oxygen, collapse this pair, fold it in, make that a double bond, and get rid of that guy. Okay, so now everybody's got an octet. It's not going to be a formal charge of 0 for the central atom or for this one, but it is for the oxygen. Okay, so if I look at that, what's the structure around that guy? So that's an AB2, and an AB2 is linear. What do I say? All right, we're out of time. Do your mastering chemistry. See you tomorrow for the test. Bring a Scantron. Meredith. No, Ross, yes.